effective length coefficient factors for braced columns. See, it says that the effective length for short columns is calculated based on the effective length coefficient. So the effective length is the effective length coefficient times the length of the column. And this effective length coefficient is a function of the end restraint of the columns at the top or bottom. So at the top, you check the condition at the top, you check the condition at the bottom. If it's 1 at the top, 1 at the bottom, your factor is 0.75. So you say at the top, in our own case, top is 1, bottom is 1 because it's deeper. Okay? So we have 0.75. Condition 2, the end of the column is connected monolithically to beams or slab on that side which are shallower. If it's shallower, condition 2 applies. Condition 3. So for shallower, if you have, for example, a column punching on a slab, if you have a column framing directly into the slab, and the slab is a 150mm slab, you see that the 150mm is shallower than 230. So that will apply. Condition 3. The end of the column contains members which, while not specifically designed to provide restraint to rotation of the column, will nevertheless provide some nominal restraint. So where you have columns, where you have column connectivity that is not providing significant restraint, condition 3 applies. And then condition 4 is when the column is unrestrained against lateral and rotational. That is, you have a free, like a free-ended column, condition 4 applies. So our own case, in many instances, we are having condition 1 top and condition 1 bottom. So we're going to use a 0.75 effective length coefficient. So go back here. ELY, we put 0.75. ELZ. FC, the characteristic material strength of concrete. So we are using a grade 30. We are using 30 460 reinforced concrete cross section. But in engineering design, because of site condition and site constraints, possibility in alteration of quality control, you need to ensure that you reduce the strength in design to cater for unprecedented contingencies in construction. You may not be the engineer involved in the construction, you may not be an engineer involved in the supervision, and you may not be able to cater for the excellence in quality control in engineering design. So you have to reduce the characteristic material strength intelligently via engineering judgment without impacting on the cost. Recall that if you so reduce the characteristic material strength, your structure may fail, resulting you to increase the cross section, which has a cost implication. So instead of using 25 megapascal, which is 25,000 kilonewton per meter square, we are going to use a reduced value of 22,000 kilonewton per meter square as the characteristic material strength of the concrete. The use strength of main reinforcement. So for our the same way, we are going to reduce the use strength, because in this country, you're designing in this country, most of the reinforcement bars, type 2 reinforcement bars to BS 4449, there's a lot of quality control reduction in this country, so you need to ensure that that is captured in engineering design so that your design is safe. So you're going to use 410 megapascal. The use strength of shear reinforcement is also 410. The maximum size of your reinforcement. Okay, so for our beams, floor beams, the maximum size of reinforcement that STAAD should consider in design should be T25. Or let's start with T20. For the roof beams, the maximum size of reinforcement that STAAD should consider in design should be T16. The minimum size of reinforcement STAAD should consider in design for slab, we'll say minimum size, we'll say T16. On the floor beams, the minimum size on the roof beam should be T12. For our columns, we also need to put this maximum and minimum size of reinforcement for columns too. So for columns, the maximum size of reinforcement should be T16. Let's see whether we've done that. I think we've done that already. The shear reinforcement should be T10. This is serviceability limit state criteria. Let's not check for serviceability limit state for now. Let's consider ultimate limit state design requirements. So that's all. The next thing you specify is your track. Track is very important in engineering design in STAAD. If you don't specify your track correctly, the extent of engineering design information you will see in the output would be limited depending on the track parameter you specify. In our own case, we want to see the detailed design calculations. So our track parameter is going to be parameter 1. Add. And that's all. So you close. As soon as you create your parameters, they will all be in question mark because you've not assigned them to any of your members. So you need to start assigning. You may have forgotten what the parameters are usually because you're not a robot, you are a human. So if you have forgotten, you always click on the question mark parameter, right click and edit. You always see what it means for you to assign. In this case, we want to assign this parameter to the columns. So what do? You select all your columns. How do you select your columns? Just click on select by beams parallel to the y-axis, view selected object only, okay, and then you assign to these beams. It assigns everything and it takes it green, which is fine. Next thing is clear. What is this clear? If you have forgotten, let me assume you are a novice, like a trainee. Right click, go to edit. It tells you what it is. You remember, you now say alright. So you assign this property to both the beams and columns. The effective length coefficient, which is ELY and ELZ, you are assigning that to the columns. Okay. The characteristic material strength of concrete, we say is 22 megapascal. We are assigning that to both the beams and columns. The yield strength of shear reinforcement, we say is 410 megapascal. We're using high steel, not mild steel. So bars are designated as T, T10, T16, T8 as the case implies. So we are applying it to the beams and columns that have shear reinforcement. The maximum size of main reinforcement we want to consider in design. For the floor beams, we are saying we want to consider a maximum size of T20 that STAAD should use in design. So in this case, we're going to select just the floor beams. Don't make a mistake. Only the floor beams, please. Make sure, what elevation is this? Elevation 11.4. Elevation 11.4. I hope it's a floor elevation. Alright, so that's the third floor. So all the floor beams, the maximum size of reinforcement we are using is T20. So you select all the floor beams. Good. The maximum size of reinforcement for the roof beams, we are saying is T16. Also, the maximum size of reinforcement for the columns too, we want to use T16 as the maximum. So we don't want STAAD to consider a design in excess of T16 for the columns. You know, for the purpose of design, if it fails, then we can proceed, we can modify our design, you know, to change it to T20 on the columns that fail. But we want STAAD to use a range of maximum reinforcement size of T16 and then minimum reinforcement size of T12 for the columns. Okay, so select the columns. Minimum size for the column should be T12. That should be considered. Okay. Minimum size of reinforcement on the floors should be T16. Minimum size of reinforcement on the floors I want to consider is T16. One would want to ask why we are looking at T12 as the minimum size of reinforcement on the columns. Note that columns are predominantly carrying concentrated loads. And if you look at the equation for column design under axial loads, you have that the design load N is 0.35 FCU AB or AC, where AC is the area of the concrete cross section. Then plus if you take into consideration the fact that you have holes in the concrete cross section, you will subtract the holes of the reinforcement, which is 0.65 FCU area of concrete plus 0.75 FY minus 0.35 FCU area of course. So you find out that the capacity of the concrete has, for an FCU equals to 30, have significant strength against compressive load. So it's except you have biaxial, uniaxial bending that makes the stress distribution on the concrete cross section changes and highly indeterminate, that your reinforcement sizes will not have to be increased. And note, because of the design requirement and the use of design charts in column design, the sizes of reinforcement on each face have to be similar. So they have to be the same number of reinforcement sizes on each face. Okay, so minimum size of reinforcement T16 for the floor beam. So we select them and add and assign. Minimum size of shear reinforcement for both beams and slab, we take it as T10. Finally, track 1 to give us the design results and design calculation results. Select all your structural entity and assign it to it. We are fine. The last thing for us to perform the analysis. Before you do that, we need to specify certain commands. You tell STAAD to design beam, add, design column, add. If you want to calculate the material takeoff, you can also select that. It can calculate the quantity of concrete for all the entire structure, but we don't want to do that for this purpose. Close. So design beam, you select all the beam elements on your model. Assign. Design column, you select all the columns. Assign. Wow, okay, I think we are all right. As soon as you're through, save your file, then run analysis. Analyze, run analysis. So in engineering design, we STAAD, or any software, be it ITER, Proton, whatsoever, they may always be potentials for errors or warning. One of your ability to troubleshoot issues with structural analysis is the potentials, the in-depth knowledge of the engineering analysis process. This will aid you in troubleshooting any possible errors that would arise in the course of analysis. In our case now, we have no error and we have no warning, which shows that our analysis is excellent. But it's saying we just have one note, So what is crucial is if you have errors. Once you have errors, it means that there's an issue with your analysis and you need to go and check it once again. So go to output. Okay, so this is just a very simple, irrelevant note. So let's go to results. So what it just tells you is that, if you choose to break your one-way loads. So if you look at what we had done is that in our load application of our loading on the structure, if you look at the roof load, you see what STAAD is just saying that you may choose to break these loads into panel by panel, but we chose not to do that. We chose to define our regions, as they apply. So that's what STAAD is saying, that it's just giving you a note about one-way loading that you may choose to break them as applied. So you go to result and then go to concrete design, which is very important to us. So I'll just explain. I'll just take a typical one beam, one column, and then I'll explain the result so that we understand. Let's use let's go to the model. Let me just take any. Okay, so I'll take a beam on the roof level, a beam on one of the floors, and then one column, and then I'll explain the result. So let's use maybe this beam. This beam what? This beam 737. Wow. Okay, let's look for beam 737. Okay, beam 737, that's this beam. Let's look at this. Let's explain. So it says length of beam is 3.93. Is it true? Let's go back. That's correct. 3.93. So it's saying that at level 1, at height 43, you need 3T16. How did he get height 43? Remember that we specified that the distance from the edge of the reinforcement to the bottom, the edge of the concrete to bottom reinforcement is about 35 millimeter. If you add 35 millimeter to the center of the reinforcement size is 16, center is 8 mm, 35 plus 8 to give you 43 mm. You see the importance of putting the parameter correctly. If the parameter is put wrong, STAAD will give you wrong output information in design. So he said at level 1, that is 43 millimeter, you need 3T16 from here to here. So let's look at let's look at the bend moment diagram so we can understand what's happening. Go to the output processor. Go to beam. Good. Look at the bend moment diagram. Let me single out this entity because we want to investigate it. Once you can investigate and understand one, you can understand what's happening in every other structural entity. Take this, view selected object only. Let's look at this. Now, remove the dimension. So look at, we have hugging moment, sagging, and then hugging. Let's investigate it further. Double click on it. Go to shear bending. Click on the load case, which is load case 19. Let's look at the load case STAAD is using for design. It says, where is it? Length this, level 1. What load case? Critical positive moment is this at this load case 19. Yes, look at the load case so that you will review their bending moment diagram to back check the design results. Load case 19. So let's go to load case 19. Aha. So let's look at what it's saying. So now let's look at this. Let's look at the node. Everything has to be checked perfectly. Let's look at the node numbers so that we can see what it's saying. Okay, so we have node 349 to 354. 349 to 354. That's good. So what is it saying now? It's saying that critical positive moment is 11.07 at 1.638. 11.07. Where is it? So you can always, let's put the distance here. 1.638. As you put it, the slider will move. So what are we having? 1.638. 11.07 at 1.638, load case 19. So 1.63, okay, I'm seeing, okay, yes, it's about 11, because if you look at this approximates to 3 decimal points. If it's to 4 decimal points, if you change it into 4 decimal points, it will give you 11. You can see this is about 11 points. It will give you that 11, approximately 11. So this gives you the analysis engine results based on analysis engine without approximation. But the environment, I put into approximation to 3 decimal points. That's why you are seeing